Happy learning! Today we're going to talk about digraphs. Okay, so before we get to defining what a digraph is, let me give you a little bit of motivation. So far, we have restricted our study to symmetric relations. Basically, the order that we write an edge doesn't matter. Right, so edge AB is equal to edge BA. But you could imagine situations where you're only allowed to travel along an edge in one direction. Like think of one-way streets, right? You could only travel one-way streets in one way. Okay, and there's also going to be situations where maybe it takes less time to travel one direction than the other, right? If you're traveling into the city during rush hour, it's going to take you a lot more time than if you were to travel out of the city during rush hour. All right, and so the way we do this, we adjust for this, is we have directions to our graphs. So in many cases, the direction we travel along the edge matters. Okay, so maybe it costs 10 minutes to travel into the city, and it costs 5 minutes to travel out of the city. And so the way we adjust for this is by defining something called a directed graph, or digraph. So a directed graph or digraph is a graph which we'll call G. It has a vertex set still, and it doesn't have an edge set. It has a new set called the arc set. Okay, so it's G equals VA. That consists of a vertex set V and an arc set A. Well, what is an arc? An arc is an ordered pair of vertices. It has a direction to it. All right, so let me give you an example. All right, so let me give you a directed graph here. We're going to have 4 vertices. So ABCD is our vertex set. And suppose we have the arc AB. So we're going to draw it with a little arrow at the end to represent that it's an arc and not an edge. And maybe we have BA. The arc DB. DA, DC, and then maybe we have a loop. All right, so in this case, our vertex set is, of course, ABCD. And our arc set, we're going to be a little bit careful here. It's an ordered pair. So the order we write these vertices matter. The first thing is going to be where the arc starts, and the second thing is going to be where the arc ends. So this arc here is the arc AB. And this arc that goes from B to A is, of course, BA. We have C going to itself. And then we have D going to A, D going to B, and D going to C. Okay, the head, so if this is our arc, X is the head, Y is the tail. Okay, so our arcs start at the head, end at the tail. And the underlying graph of a directed graph is just the graph formed by replacing all of the arcs with edges. So the underlying graph for a digraph is the graph formed by replacing all the arcs with edges. Okay, so just real quick down here, the underlying graph would be, well, we replace these two arcs with edges. It would be this graph. Okay, so it's just basically we have this and we lose the information of what direction the arcs go. All right, so what we're going to look at now is we're going to look at the traveling salesman problem, but not on graphs, but on directed graphs. So this is called the asymmetric traveling salesman problem. All right, and so what is the goal? Our goal is to find an optimal Hamiltonian cycle. So we visit each vertex exactly once on a directed graph. All right, so that's our goal, is to find a optimal, so the shortest length Hamiltonian cycle on a directed graph. But in order to do that, to try to answer this question, we do need a little bit of notation. So we've talked about a complete graph. That's a graph that has all possible edges between the vertices. A complete digraph is similar to a complete graph But it's not just an edge between the two vertices. There are two arcs between any pair of vertices. One going this way and one going the other way. So it's similar to the complete graph, but with the added condition that between any vertices, x and y, both arcs xy and yx exist. Okay, so we're going to have arcs between all possible pairs of vertices. All right, and so for example, the complete directed graph doesn't get a fancy letter like kn. We could give it a letter if we wanted to, but so the complete digraph for n equals 1 is just a point. Right? There's no pairs of vertices, so there's nothing to put arcs between. For n equals 2, we have these two vertices, and between the two vertices, we're going to have an arc going one way and the other. For n equals 3, you can see it starts getting pretty messy with n equals 3. And then n equals 4, I'll draw it. But there's a lot of arcs for n equals 4. N equals 5, there's even more. Okay, so it gets out of hand pretty quick. And so our goal is we're going to use some of the algorithms that we discussed in previous videos to find maybe not the most optimal Hamiltonian cycle, but good enough Hamiltonian cycles for most practical purposes. All right, but all of our algorithms involved using graphs, not directed graphs. And so what we're going to do is we're going to do something called the undirecting algorithm. And it's going to take a graph and it's going to give us a new graph that doesn't lose any of the information from our directed graph. Right? When we found our underlying graph, we lost some information, right? We lost which ways the arcs were pointing. This undirecting algorithm is going to make it so we don't actually lose any information when we use this. All right, so let me walk through this undirecting algorithm, and then we will see an example of how it's used. Okay, so what is the input for this algorithm? It is a weighted complete graph complete directed graph, sorry, which we could call G, which has a vertex set, an arc set, and some weights. All right, so how does this work? The first step is we're going to take every vertex in our graph and make a clone. All right, so we're going to have, for each vertex, we're going to have it and its clone. And then we're going to put an edge between a vertex and its clone. So we're going to add this edge x prime to our new graph. And the weight of that edge is going to be 0. All right, so that's our first step. Is if we started with 2 vertices, our new graph is going to have 4 vertices. Step 2. For each arc, xy, form an edge x prime y. Okay, so if the arc goes from x to y, in our new graph we're going to have an edge from x prime to y. And the weight will just be the weight of the arc xy. Okay, so for each of these arcs, we're going to have a new edge x prime y, and the weights are going to stay the same. If we do this for all of the arcs, the output is going to be a weighted clone graph. All right, let's take a look at an example. So suppose we have the following weighted directed complete graph. All right, and then we have these arcs, 11 and 12. This arc has 8 and coming back 9. Okay, I know it's a little bit messy, but bear with me. Our goal, and so let's name these. This is H, G, T, L. All right, our goal is to get the clone graph. Our directed complete graph here has 4 vertices, so our clone graph, let me hear it in the comments, will have 8 vertices. All right, so let me draw our clone graph. This will be H, and its clone H prime. This will be G, and its clone G prime. Not sure what that was. This will be T, and its clone T prime. I've lost my mind. The thing I erased. Oh my God. T, T prime, and this is L and L prime. Form an edge between each vertex and its clone with weight 0. Okay? And now for each of the arcs, we're going to make an edge. So for instance, this arc goes from G to T. So that's going to correspond to the edge G prime T. And it has a weight, the same weight as we have here. Right? You see how this works? This arc goes from T to G. So we're going to go T prime to G, keeping the weight the same. And we have to do this for all of the arcs. All right, so here we go from T to L, so that's going to be T prime L. And then L to T, so L prime to T. L to H, H to L, which would be H prime to L, H to G, which is H prime to G, and then G to H has 4. And we still have to do the diagonal ones. So G to L, so that's G prime L. That's going to have G prime to L that has 12. And then L to G, L prime G is going to have 11. All right, and then there's 2 more. H to T, so H prime T is 9. Okay, I wrote HT prime. So T prime H, that should be this one, that's 8. And then H prime T is 9. Okay, this here is just a graph. It's not a directed graph anymore. It captures all of the information. It captures all of the information that our directed graph has, but now it's a graph, so we can apply some of our algorithms to it. All right, so what I want us to do now is I want us to apply the nearest neighbor algorithm to this graph starting at H. Okay, we're going to do it on our clone graph, and then we're going to describe it in terms of the directed graph, because the directed graph is really what's happening in real life. All right, so here's our clone graph. And we're starting at H. What is the nearest neighbor to H? It's H prime. Okay, what is the nearest neighbor to H prime? L. What is the nearest neighbor to L? It's L prime, right? Length 0. What is the nearest neighbor to L prime? Well, it's either H or T. We can't go back to H because we want to hit every single vertex before completing our cycle. So it's T. What's the nearest neighbor to T? Is of course T prime. What's the nearest neighbor to T prime? Well, we would like to go to L, but we can't do that one. We would like to go to H, but again, we can't do that one because it would close off the cycle too soon. So we have to go up to G. And then you could check, but the last thing that possibly could work is going back to H. All right, so that's our Hamiltonian cycle on the clone graph. But to do it on the directed graph, so we have H, G, T, and L. You could ignore all of the steps that have length 0. Those don't actually correspond to anything in our directed graph. We're going H prime to L. Remember, H prime L means we start at H and go to L. L prime t means we start at L and go to t. T prime g means we start at t and go to g. And g prime h means we start at g and go to h. All right, and so the total weight here is 23. All right, so the undirecting algorithm allows us to take a directed graph, turn it into just a graph, and then apply some of the algorithms that we've talked about in previous videos. Okay, well, that's all I have for today, so let me know in the comments if you have any thoughts or concerns. I hope the course is going well for you so far. I'm really enjoying making these videos, and I will see you next time. Take care. Bye-bye.